In the last video, we ended with a discussion of measuring the width of a peak. Now I want to get into why there is a width to begin with, what we can do to cause it to be more narrow, and why that would matter. The explanations are very visual, so we're going to be slide heavy for a while. Just note that slides 10 through 13 have to do with the width of a peak. And with that, let's get into it. So on this slide, what we have are two different columns, each containing the same single chemical. So I'm not worried about having two or more solutes and talking about separations. I want to just focus on explaining why this compressed band of the same chemical will start to spread out as it travels through the column. And then I want to contrast these two columns, where the only difference is how densely packed they are with those stationary particles, the stationary phase that we discussed earlier. So I'm going to start by showing what would happen as we flowed this red solute through the left column, the less densely packed column. Here we go. We can see the solute starting to spread out. And this is because some of the particles are interacting less with the stationary phase, and others are interacting more. Even though they're all the same type of chemical, some just happen to interact more and others less. And as they exit, our peak forms, and we've seen this animation before. And we should now understand what this peak represents, right? The very start of it represented when the first red particle came out of that column. The peak, which marks the retention time, corresponds to the middle of the band, where the band is most concentrated with those red particles. Then the end of the peak represents the last particles exiting the column. And these are the particles that were interacting with the stationary phase more than the rest, and that's why they came out last. You might be wondering at this point why some of those solute particles will interact more with the column and others less with the column, and we'll get into that in the next slide. But first, let's quickly contrast what happened here with what's going to happen in a column with a more densely packed stationary phase. Here we go. We begin flowing the solutes, and it turns out the higher density of the stationary phase increases the interactions with all of the solute particles, and as a consequence, the solutes don't spread out from each other as much. The result is we're going to get a narrower peak in the chromatogram. And there it is. Because the particles didn't spread out as much this time, the peak is more narrow because they were detected over a shorter period of time. Now the next concept to address is why a column with a more densely packed stationary phase would ultimately lead to a tighter, more narrow peak. And as we learn about that, we will also learn about why some solute particles just happen to interact less with the stationary phase and others interact more with it. Let's make an analogy. Imagine we have a race between four genetically identical Hokies. They have the same build, they can move at the exact same speed, and there are these hurdles in their way. And we can see the hurdles have a relatively even distribution throughout that field. We don't have a situation where one part of the field just has this cluster of hurdles, right? They're pretty evenly distributed. However, one Hokie just happens to be lucky and only one hurdle is directly in their path. These two Hokies represent the average. They have two hurdles in their path. But this Hokie is unlucky and happens to have three in their path. Well, what can you do? In this situation, who are you going to bet on to win, and who's going to be the biggest loser? Well, let's find out.
Don't stop me now. I'm having such a good time. I'm having.
And no shocker. So notice this spread. The majority of our Hokies are in the middle of this distribution. The lucky Hokie that was least impeded is in the front, and equally far behind is the highly impeded Hokie. Now, let's make that field more densely packed with hurdles. Now, all four of our Hokies have more impediments in the way. That said, the first Hokie still happens to have the least amount of hurdles to clear, and the third Hokie still has the most. But now let's see what happens in this race.
And they're off. The average impeded Hokie one taking an early lead, but here comes the less impeded Hokie right on his heels. Meanwhile, the most impeded Hokie is a loser.
we still have a similar distribution. The majority of the Hokies are in the middle. We have one that got ahead, and the most impeded lagged behind. However, notice how much tighter that spread is than before. See what I mean? In the less densely packed field, the spread was a lot larger, and it comes down to the fact that the highly impeded Hokie had 3 times as many hurdles to get over as the least impeded Hokie, whereas in our more densely packed situation, in which each of our Hokies had to clear 2 more hurdles than in the previous situation, well, the relative difference between these two situations just got a lot smaller. This is no longer 3 times larger than this. It's not even twice as many hurdles as what the top Hokie had to deal with. And this is the essence of why a more densely packed column has a tighter distribution of solute particles compared to a less densely packed column. It's the exact same concept. Some of the solute particles just don't have to deal with as many stationary phase particles as others, but we can minimize these discrepancies by packing the column more densely. Now let's get into why all of this matters. So imagine we have our 2 columns, and quickly ask yourself which of these is going to lead to a smaller spread of the solutes. And while you're at it, quickly ask yourself which situation do you think is more preferable, a larger spread or a smaller spread, given that this is ultimately supposed to separate 2 or more different chemicals from one another. And the answer is this column that's more densely packed will limit the spread of solute particles, which is better for separating 2 different chemicals from one another. So notice we are back to having 2 solutes. We have a green band of solute particles up front, and behind it is this red that you can just barely make out right now. But we'll be able to see it better once we start flowing them through this column and they separate. I'll start with the left column. Here we go, and we see green is getting ahead of red, but they're both spreading out so much that they never fully separate. And so the result is each of them would come out and be detected, but there is a period of time where both chemicals are coming out on top of each other. And this is going to lead to convolution. What the instrument's really going to show is just 2 humps kind of merging into each other, and this data is not easy to analyze. On the other hand, let's see what happens on the right column. Green separates out from red, and while they are both still spreading out, they are clearly coming out at different times now. There is no convolution. And the key to that was because we had this more densely packed stationary phase, the green and red solutes weren't able to spread apart as much for the reasons we went through with that whole Hokie hurdle analogy. And that allows for the peaks to be more narrow and have less chance of overlapping, and so we don't have convolution. The peaks are well separated. This is good. And so to introduce some chromatography terminology, we would say that this column over here that did a better job of separating our chemicals has more theoretical plates than this column over here. So what does that mean? Why am I talking about plates all of a sudden? Well, this terminology goes back to a different type of separation column known as a distillation column. And that's pictured over here. So in these older columns, we would have a series of plates or stages that we would put a mixture through. And the more plates there were, the better the compounds in that mixture would separate from one another. Now a chromatography column, like the ones we've been describing, don't have any plates, they have these stationary particles. But we still describe how well these particles can separate compounds from one another by how many theoretical plates exist within this column. So here's what I mean by all of this. Imagine we had 2 different distillation columns. This one has more plates than this one. Well, then this column is going to do a better job of separating our chemicals than this column over here. And that's analogous to what we saw with the more densely packed column versus the less densely packed column. Better separation over here. And so we would say that this column here has more plates than this column, even though, one more time, there are not actually any physical plates in those columns. It's just surviving terminology from the olden days when these types of columns were used. So bottom line is more plates, quote unquote, means a better separation of the species. But since there aren't actually any physical plates in a chromatography column, we describe them as theoretical plates. And there's a formula for calculating how many theoretical plates a column has. And we're going to learn that formula momentarily. The main thing to keep in mind is the bigger the number we calculate, the better the column is at separating its chemicals from one another. So let's get into that formula. On the left side of the equation, we will write N, and this stands for the number of theoretical plates. Number of theoretical plates. And remember, the larger that number is, the better our separation. This number is going to be equal to 5.55 times the retention time of the species in question squared, all over that species half-width, also squared. And we can calculate the height of each of these theoretical plates with the following formula. H equals L over capital N, where L represents the length of the column, capital N is just the number of theoretical plates, and H represents the height of the plate. Height of plate. And what I mean by that is if we actually had a column that was literally full of these different plates that are used to separate our chemicals, and again, I can't stress this enough, these don't actually exist. They existed in those older tools, and we just refer to our new chromatography columns as if they were present, but they aren't. But if they were present, H would represent the height or the distance between those plates. So quickly ask yourself, do you want that number to be larger or smaller? And the answer is we want it to be smaller. And let's go through the logic. Let's actually start over on the left where we had this formula for N. Do we want more or less plates? You should be able to say at this point, we want more plates. Greater plates, greater separation. And we can see there's an inverse relationship between the height of a plate and the number of theoretical plates there are in a column. And so if we want more plates, that means we want smaller height. This in turn will lead to a more narrow peak as the solute exits a column. More narrow peak, which as we saw in the previous animation, means that we'll have a better separation of solutes. Better separation. So we will end the video at this point, and for that matter, this point represents the end of exam 3 material. Anything I cover from here on out will only show up on the final, but will still be related to what we have been discussing so far, which is fair game for exam 3.